All right, what do you think?
Okay.
Problem number 1. The Earth is 1.49 times 10 to the 11 meters from the Sun. If the solar radiation at the top of the Earth's atmosphere is 1,340 watts per meter squared, what is the total power output of the Sun? Okay, so the radiation on the top of the Earth's atmosphere is 1,340 watts per meter squared. With those kind of units, watts per meter squared, we're really looking at intensity. So in problem number 1, we're seeing that the intensity at the Earth's atmosphere is 1,340 watts per meter squared. And that's the power per area that's hitting the Earth's atmosphere. We can imagine, though, that using the definition of power is equal to the intensity times area, or intensity is power per area. And so the power of the Sun would be the intensity times the area that this power is being distributed over. Now, it's not just this area. This is the intensity from the Sun itself. So if we imagine that the Sun is putting out a certain amount of power, and the area it's being distributed over is the area of a sphere of radius from the Sun to the Earth. That's the intensity that the Earth is receiving in its atmosphere. So what we're talking about, this area is the area of this sphere, which is 4 pi r squared. So we'll say that the power of the Sun is the intensity times 4 pi r squared. I'm using a script P because later on we're going to use a different P for pressure. So I'm using script P for power. So this would be 1,340 watts per meter squared times 4 pi times the radius of this circle, which was 1.49 times 10 to the 11 squared, gives us 3.74 times 10 to the 26 watts. So quite a lot of watts from the Sun. Problem number 2. If the radiant energy from the Sun comes in as a plain electromagnetic wave of intensity 1,340 watts per meter squared, calculate the peak values of the electric field and the magnetic field, E and B. Well, intensity is equal to the speed of light times the energy density, and we're representing the energy density by U. The energy density has a value equal to 1/2 epsilon naught times the maximum E field squared, or the energy density is the E field squared times 1/2 times the epsilon. And so in this case, we can solve this for the maximum E field because we're given the intensity in this problem, and of course we know what the speed of light is. So we'll say the intensity is equal to the speed of light times 1/2 permittivity of free space times E max squared. Solving this for E max, that would be 2 times the intensity divided by the speed of light, epsilon naught, square root. So that's 2 times 1,340 over the speed of light times the permittivity of free space, 8.85 times 10 to the minus 12 square root, and that gives us 1,005 volts per meter. So that is the electric field, the maximum electric field of this electromagnetic wave. We want to also find the maximum magnetic field, and the maximum electric field relates to the maximum magnetic field, again by the speed of light. Or the E field equals the speed of light times the magnetic field. So magnetic field equals E max divided by the speed of light. And so this will be 1005 divided by 3 times 10 to the 8. It's 3.35 times 10 to the minus 6 Tesla. Here's an interesting note. We said that the energy density is 1/2 epsilon naught times E max squared. And we said that E max equals E max divided by C. So, we also know that another way to define the energy density is 1/2 1 over mu naught E max squared. So just as an interesting sidelight, if that's that, and this equals this as well, if we set these two equal to each other, then I would have 1/2 epsilon naught E max squared equals 1/2 1 over mu naught E max squared. Get rid of the 1/2. Divide both sides by epsilon naught, and realize that E max equals C B max, so we have C squared B max squared for this equals 1 over epsilon naught mu naught B max squared. Get rid of B max squared on both sides. Take the square root of both sides, and you get this speed of light is equal to 1 over the square root. I can fit it down in here. Of epsilon naught times mu naught. So with those definite values, those definite constants that you can find on the cover of your book, just an interesting idea. At 8.85 times 10 minus 12 times 4 pi times 10 minus 7, take the square root, 1 over that, get the speed of light. Problem number 3, if the maximum E component of an electromagnetic wave is 600 volts per meter, what is the maximum B component? All right, problem number 3, maximum E component is given as 600 volts per meter. The maximum B component is the E max divided by the speed of light. So that's going to be 600 divided by 3 times 10 to the 8. And that gives us 2 times 10 to the minus 6 Tesla. Answer C. Problem number 4. Find the force exerted by reflecting sunlight off a reflecting aluminum sheet in space if the area normal to the sunlight is 10,000 meters squared and the solar intensity is 1,350 watts per meter squared. All right, so on this problem number 4, we are given that the intensity is 1,350 watts per meter squared. And from the intensity we can get the energy density, since I equals CU, ICU. The energy density is the intensity divided by C. So that's 1350 divided by 3 times 10 to the 8 is 4.5 times 10 to the minus 6 joules per cubic meter. And an interesting idea is that the pressure of either reflecting or absorbing surface is related to the energy density. They have the same units, because if you think of energy density, that's joules per meter cubed, and if you were to switch this, say if you switch joules into Newton meters, then meters will cancel out top and bottom, and you'd have newtons per meter squared. So the units of this is the same as newtons per meter squared, which is the units of pressure. So pressure relates to energy density. And in particular, if the surface is absorbing, then the pressure will equal the energy density. And if the surface is reflecting, as in this case, the pressure will equal twice the energy density. So in other words, pressure equals energy density if absorbed completely, and pressure equals twice the energy density if totally reflected. So in this case, we're going to use this version right here. We have a totally reflected off aluminum sheet, and so our pressure will be 2U, 2 times 4.5 times 10 minus 6, is 9 times 10 to the minus 6 newtons per meter squared. And we want the force on this aluminum sheet. Force equals pressure times area. So that would be 9 times 10 to the minus 6 newtons per meter squared times the area of this sail, which is 10,000 meters. So this would be 0.09 newtons. Not a very large force, even for this reflecting sail, but at least it's a consistent force, and you could build up speed pretty quickly if you applied this force for some time. Problem number 5, a solar cell has a light gathering area of 10 square centimeters and produces 0.2 amps at 0.8 volts DC when illuminated with an intensity of 1,000 watts per meter squared sunlight. What is the efficiency of the solar cell? All right, so we're going from the last problem, which was a solar sail, to this problem, which is a solar cell. Oops. And whenever I think of efficiency, I think of gain over give. So I just define efficiency, in this case, would be the power that we gain over the power that we give. And what we gain is what's going to be the output. And it says it produces 0.2 amps at 0.8 volts DC. So our power that we gain is going to equal current times voltage. 0.2 amps times 0.8 volts is 0.16 watts. That's what we're going to gain. And the question is, what are we given? And that is what's coming from the intensity of the sunlight itself. And so we can say that our power that we give will equal that intensity times the area. And that intensity is 1,000. It's designated by the pointing vector S, but it's the same as what I'm using for I here. So the S equals 1,000 watts per meter squared is what the intensity is. The area that we're putting this over is 10 square centimeters. That's going to be 10 times 10 to the minus 4 square meters. And so that will give us 1 watt. So this is what's coming in, 1 watt. This is what we're getting out of it, 0.16 watts. Our efficiency, as I said, is what we gain over what we give. Gain over what we give. So that'd be 0.16 over 1, or 0.16, or 16% efficiency. We lose 84% of the possible energy, which is not bad because we're losing that anyway. If it's out in space, it's free. It's unlimited, free, nothing to worry about in that sense. Problem number 6. A 100 kilowatt radio station emits electromagnetic waves in all directions from an antenna on top of a mountain. What is the intensity of the signal at a distance of 10 kilometers? All right, so I need another one of these. We have the power is 100 kilowatts. So that's going to be 10 to the 5 watts. And we have a radio station on the top of a mountain. And it's emanating in all directions. And we want to find the intensity at a distance of 10 kilometers. So we can imagine if it's radiating in all directions, this power that we just calculated is being distributed over a sphere of radius 10 kilometers. And the area of that sphere is 4 pi r squared. So intensity is power divided by area. So that's going to equal 10 to the 5 watts divided by 4 pi r squared. R in this case is 10 kilometers. So that's going to be 10 to the 4 meters squared. So it's 10 to the 5 over 4 pi times 10 to the 8. And that's going to be an intensity of 7.96 times 10 to the negative 5 watts per meter squared. So anywhere on that sphere is the intensity that you would receive. Problem number 7. Determine the amount of energy carried in 1 meter of a 3.5 milliwatt helium neon laser beam if the cross-sectional area of the beam is 5 times 10 to the minus 6 square meters. All right, let's take a look at this one, problem number 7. For a marker. Power is 3.5 milliwatts. So we'll say the power is 3.5 times 10 to the minus 3 watts. And power, well, let's just keep that in mind. We're interested in the energy density, and we're going to select a 1 meter length piece of space which has a cross-sectional area. Now the area was given as 5 times 10 to the minus 6 square meters. We may or may not need that, but we're going to envelop some energy density within this cylinder, so to speak, in the laser. And I could say that the total energy contained within that volume is the energy density, the energy per volume, times the volume of that. All right, so there's the energy density, energy per volume times the volume of this piece of space is the total energy that I have within that space. But my energy density is the intensity divided by the speed of light, and my volume is the volume of this cylinder, which is the area, cross-sectional area, times the length, which I know to be 1 meter, but I'm just going to put in length L there for the time being. Intensity is the power times the area. I'm sorry, power per area. So we have the power per area times C times the area times the length. That's the area actually cancels out, so we didn't actually need to know the area of the beam. So this is going to be the power times the length over the speed of light. That would be 3.5 times 10 to the minus 3 times 1 meter over 3 times 10 to the 8. And that gives me 1.17 times 10 to the minus 11 joules. So that is the energy contained in 1 meter of a 3.5 milliwatt helium neon laser. Problem number 8. how much electromagnetic energy is contained per cubic meter near the Earth's surface if the intensity of sunlight under clear skies is 1,000 watts per meter squared? All right, so let's think about this. We have intensity as 1,000 watts per meter squared. So it's basically saying that some of that intensity that hits the Earth's atmosphere is going to be attenuated. And this is what we actually get if we were to try to collect it near the Earth's surface. Energy density is the intensity divided by the speed of light. So it would be 1,000 divided by 3 times 10 to the 8. It gives us an energy density of 3.33 times 10 to the minus 6 joules per cubic meter. But we want to find the energy contained in 1 cubic meter. Here's the energy density. And so we basically could say that the energy is equal to the energy density times the volume that we're considering, which is 1 cubic meter in this case. So it's going to be 3.33 times 10 to the minus 6 joules per cubic meter times 1 cubic meter is 3.33 times 10 to the minus 6 joules. So you would need a considerable amount of cubic meters to start collecting some energy from the sun. Problem number 9. At a distance of 10 kilometers from a radio transmitter, the amplitude of the E field is 0.2 volts per meter. What is the total power emitted by the radio transmitter? All right, so we have a amplitude of the E field is given as 0.2 volts per meter, and the energy density is by definition 1/2 permittivity of free space epsilon naught times the amplitude of the field squared. So in this case, this would be 1/2 times 8.85 times 10 minus 12 times 0.2 volts per meter squared. And that gives us 1.77 times 10 to the minus 13 joules per cubic meter for the energy density. We want the total power transmitted by the radio transmitter. This is the energy density. The intensity relates to the energy density by ICU. So this intensity is the speed of light times the energy density. And I went one better because, well, let's actually come up with a number for that. .31 times 10 minus 5 would be watts per meter squared. But intensity equals power per area. So power would equal intensity times area. That's going to be 5.31 times 10 to the minus 5. The area we're talking about is the area of a sphere at a distance, in this case, of 10 kilometers from this radio transmitter. So we have 4 pi times 10 kilometers, 10 to the 4 meters squared for the area. And that will give us a total power of 66,727 watts, or about 67 kilowatts. Answer B. Problem number 10. What's the maximum radiation pressure exerted by sunlight in space with a Poynting vector or intensity of 1,350 watts per meter squared on a flat black surface? Well, in this one, we're given the intensity. (1,350 watts per meter squared). And as I said before, the pressure has the same units as energy density. And energy density is equal to the intensity divided by C. Let's actually figure out what that is. 1,350 divided by 3 times 10 to the 8 gives us 4.5 times 10 to the minus 6 joules per cubic meter. We're going to have a flat black surface, so the surface is going to be totally absorbing, and under those conditions, pressure equals the energy density for a black surface. So this pressure is 4.5 times 10 to the minus 6. Now, joule is a Newton meter, so let's write it like that, Newton meter over meters cubed. Let's take out one of these meters, so it's actually newtons per meter square, which is the units of pressure. So the pressure equals the energy density, 4.5 times 10 to the minus 6 pascals.
Right, ready.
11. What is the maximum radiation pressure exerted by sunlight in space? Pointing vector of 1,350 watts per meter squared on a highly polished silver surface. Well, in this one, we have a highly polished silver surface, so our pressure is 2U because of the reflection off of the surface. So everything else being the same, this is 2 times 4.5 times 10 to the minus 6, or 9 times 10 to the minus 6 newtons per meter squared. 9 times 10 to the minus 6 pascals. Answer C. 12. Find the frequency of X-rays of wavelength 1 angstrom equal to 10 to the minus 10 meters. All right, so we're given the wavelength 1 angstrom, 10 to the minus 10 meters. Now, X-rays is part of electromagnetic radiation, so it travels at the speed of light, and speed of light is the wavelength times the frequency. So the frequency is the speed of light divided by the wavelength. That's 3 times 10 to the 8 divided by 10 to the minus 10. So that's going to be 3 times 10 to the 18 hertz. Very high frequency. With higher frequency comes higher energy, and that's why X-rays are more energetic. 13. Green light has a wavelength of 5.4 times 10 to the minus 7 meters. What is the frequency of this electromagnetic wave in the air? All right, so we're given the wavelength of green light, 5.4 times 10 to the minus 7 meters. And again, we can find the frequency, since green light, like X-rays, is electromagnetic radiation, light, travels at the speed of light. So the frequency is the speed of light divided by the wavelength. And this would give us a frequency of 5.55 times 10 to the 14 hertz. Since the energy does go as the frequency, if we quickly compare these on the order of magnitude, the X-rays was about 10,000 times higher frequency than the green light, hence that much more energy. 14. An FM radio station broadcasts at 98.6 megahertz. What is the wavelength of the radio waves? Well, we're given the frequency, 98.6 megahertz, which would be 9.86 times 10 to the 7 hertz. And since the speed of light equals the wavelength times the frequency, the wavelength will equal the speed of light divided by the frequency, 3 times 10 to the 8 over 9.86. times 10 to the 7. And that gives us a wavelength of 3.04 meters. A meter being a little bit longer than 3 feet. So we're talking about a wavelength that's about 10 feet long for this FM frequency. So imagine if you're picking up that frequency, the waves that are traveling through the air are 10 feet long. Problem number 15. What should be the height of a dipole antenna of dimensions 1/4 wavelength if it is to transmit 1200 kilohertz radio waves? Well, our frequency is 1200 kilohertz. That's 1.2 times 10 to the 6 hertz. And so the wavelength is the speed of light divided by the frequency. 3 times 10 to the 8 meters per second over 1.2 times 10 to the 6 per second. And that gives us a wavelength of 250 meters. Since our antenna is 1/4 the length of a wavelength, that's going to be 250 divided by 4, or 62.5 meters long for our antenna. Number 16. The magnetic field of a plane polarized electromagnetic wave moving in the z direction is given by B equal 1.2 times 10 to the minus 6 sine 2 pi of z over 240 minus t times 10 to the 7 over 8 in SI units. Was the maximum electric field. All right, so we have a wave function. We're describing a wave function of a wave that's traveling at the speed of light, but the wave itself has electric vector and magnetic vector, and those are perpendicular to the direction of the motion. So that's our plane wave. And the function is magnetic field function is given by 1.2 times 10 to the minus 6 sine 2 pi z over 240 minus t times 10 to the 7 over 8. All that. That's our magnetic field. And the question is, what's the maximum electric field? Now, if this is our magnetic field function, the maximum of this magnetic field will correspond to when the sign of whatever's in here, the sign itself is 1, because that's the largest that the sign can be. So our maximum magnetic field is the coefficient out front, and so we would say that that's B max. But we know that the electric field relates to the magnetic field. It's equal to the speed of light times the magnetic field. So E max should equal the speed of light times B max. And in this case, that'll be 3 times 10 to the 8 times 1.2 times 10 to the minus 6. So that'll be 360 volts per meter. So that is the maximum electric field, 360 volts per meter.
Great.
Problem 17. The magnetic field of a plane polarized electromagnetic wave moving in the z direction is given by B equal 1.2 times 10 to the minus 6 sine of all that stuff in SI units. What is the frequency of the wave? All right, so basically we're looking at something like this. B max sine kx minus omega t. This is a wave function, just like the wave function that we were describing way back in chapter 16 of the previous course in Physics 2. In this sense, omega is 2 pi times the frequency of the wave. So if we were to look at this wave function, which is the same wave function we had here, I don't know if you can still see that. Yeah. We could identify omega as whatever's in the sine function in front of the t, and the t is right here. So our omega, which is 2 pi f, is equal to 2 pi times 10 to the 7 over 8. So the frequency is 10 to the 7 over 8, which I could write as 10 divided by 8 times 10 to the 6, which would be 1.25 times 10 to the 6 hertz. So that's our frequency. That is answer C. Problem 18. The magnetic field of a plane polarized electromagnetic wave moving in the z direction is given by B equal 1.2 times 10 to the minus 6, sine of all that stuff, in SI units. What is the wavelength of the electromagnetic wave? All right, so on this one, we're going to do the same sort of thing, but we'll re-identify what's in front of the x value here is the wave number. By definition, wave number is 2 pi over the wavelength. So the wavelength is 2 pi over the wave number. And in this case, see our k, if we look at this, our k is 2 pi over 240. And right there I could probably identify what the wavelength is just by seeing it. But if I didn't see that right away, I'd continue this and say 2 pi over 2 pi over 240. 2 pi's cancel, and I have wavelength of 240 meters. That's one way to do it. The other way to do it is say that the wavelength is equal to the speed of light divided by the frequency. We just got the frequency on the previous problem. So that would be 3 times 10 to the 8 divided by 1.25 times 10 to the 6. That also gives us 240 meters for the wavelength. Problem 19. Same setup. The magnetic field of a plane polarized electromagnetic wave moving in the z direction is given by B equal 1.2 times 10 to the minus 6, sine of all that, in SI units. What is the speed of the electromagnetic wave? Have we already introduced this one? All right, so we want the speed of this wave for 19. From the previous two problems, 17 and 18, we found the frequency to be 1.25 times 10 to the 6 hertz. And then we found the wavelength to be 240 meters. And so the speed of the wave will be the wavelength times the frequency. I already designated by C because I have a good feeling about this. 240 times 1.25 times 10 to the 6 gives us 3 times 10 to the 8 meters per second. The speed of light, as all electromagnetic waves travel at the speed of light, 3 times 10 to the 8 meters per second.